second part of presentation. How can I go to kaydediyorum ama çıkamıyorum buradan. Escape ile yapsam çıkamıyorum. Ana ekranımı göremiyorum şimdi. Windows'a bassam gelir mi? Geldi. Evet. That's the presentation. I think you are seeing this presentation page currently, right?
Yes.
Tamam, güzel, sağ olun. We were studying the internal architecture of 8086. That's the general diagram, and I have mentioned. I gave an overview of internal architecture, and we will go into details. And to be honest, there are lots of information on the slides, and some of them is repeating itself over and over again. I have already mentioned many of them. And if you remember, in the second week, I told you that due to the pipelining, due to the instruction queue, 6 bytes long instruction queue inside the internal part of 8086, it was capable of carrying out. It was capable of carrying out the operations parallelly. What I mean is that instruction queue, if you remember, the bus interface unit was taking 1 byte information and feeding into instruction queue, and execution control unit is getting that information, and it was trying to decode it, and decoding takes time. And during that time, bus control logic, the bus interface unit goes and fetches another byte of data and pushes into instruction queue. So during the execution unit's decoding time, parallelly, the next byte has been fetched by the bus interface unit into the instruction queue. And after decoding what the instruction is, for example, in the case of increment AL example, there is no need to get any other information. After decoding that, it understands what it has to be done. Then it goes and takes the information of AL and increments and puts it into back. And of course, all these operations takes time. During that time, bus interface unit goes up and fetches another byte from the memory and fills up the instruction queue. So every time the execution unit is dealing with decoding and executing, the data bus will be idle. Instead of 2 of them, bus interface unit and execution unit works parallelly. They are separated. Their I don't want to say the circuitry, but their operation control. So while one of them is working on decoding and executing, the other one is going up and fetching data and filling up the instruction queue, and that is called pipelining, by the way. And with the help of instruction queue, the operations are carried out parallelly. That means 8086 employs parallel processing, means because of the bus interface units fetching data all the time and filling up the instruction queue, allows us to process the data parallelly. And as I told you before, it has got two parts: bus interface unit and execution unit. And CPU is the main function is fetching data, decoding it, and executing it. And I always tell this, and this is the main function of CPU. And bus interface unit handles all transactions of data and address on the buses for execution unit. So execution unit doesn't interfere with fetching data. It's just decodes and executes whatever it is necessary. Fetching operation is done by bus interface unit. Bus interface unit performs all bus operations as instruction fetching, reading and writing operands. When it says instruction fetching, actually it means getting the opcode. Opcode is the instruction. What microprocessor should do will be told by opcode, and any data related to that opcode will be called operand. So bus interface unit performs fetching the opcode and fetching the operands of that opcode from the memory and calculating the addresses of the memory operands. Of course, in order to fetch the data, we need the address of that data from the memory. So we have to prove it. We have to calculate the memory address. So there is another addition circuitry here in order to produce the exact real or physical address of memory space that we want to fetch the data, fetch the operand or fetch the opcode. Sorry. Execution unit executes instructions from the instruction system byte queue. So there is no direct connection between execution unit and address data bus, the outside of microprocessor. Everything is done by data fetching. Data communication has been isolated by bus interface unit. So execution unit is isolated from the outer part of microprocessor, the outer world from the real world. Execution unit is completely isolated. Okay, it is stating the same thing over and over again. It is responsible of decoding and executing the instructions, and because of dividing the works between bus interface unit and execution unit speeds up the processing because of the parallelism. Main components of execution unit is instruction decoder, control system, arithmetic logic unit, general purpose registers, flag register, pointer, and index register. So, as I showed you before, there are registers, arithmetic logic unit, control system, and there is an instruction decoder. And in the main diagram, it was saying that execution unit control system. So it means it includes the instruction decoder as well. Instruction decoder translate instructions fetched from memory, and according to that, execution unit carries out a series of actions, and we have talked about it earlier. Control system generates timing and control signals to perform the internal operation. So, as I told you before, in order to, from the example of increment AL, all the necessary informations, all the necessary signals has been produced by the control system to fetch the data from AL register to arithmetic logic unit, and arithmetic logic unit will be doing the necessary calculations, and the results will be put back into AL register. So putting back operation will be controlled by control system. Arithmetic logic unit, as you know, it is responsible from arithmetic and logic operations, and it has got 16-bit. I mean, those operations are 16-bit. It can carry out 8-bit or 16-bit operations, and so the total length is 16-bit. These operations can be addition, subtraction, multiplication, division, and or, as I told you before, increment, decrement, shift, rotate, etc. All those binary operations can be carried out in the arithmetic logic unit. Yes, there are, I mean, we are heavily depend on the registers inside 8086. Those registers are crucial for us because otherwise we cannot, we cannot carry out any other operations. I mean, everything depends on the registers, and the main difficulty while programming in assembly language is that you don't have too many options. You have got limited number of registers. What I mean is, while writing a program in C, you can define as much variable as you want. But while writing a program in assembly language, the number of accessible variables will be, directly accessible variables will be the ones in the registers. And in the meantime, those registers, you are not completely free to use all those registers as you wish. Every register has a certain functionality. So if we are using it in force, I mean, for example, if we are using AX register for to hold if you are using AX register to hold a certain value as a variable, but if you use a division operation, for example, then that value has to be stored somewhere else, transferred to somewhere else, then use the division. The content of AX register will be changed because of that operation. Then you have to store the output of division operation somewhere else. Then you reload the variable which is stored in your AX register back into the AX register. So what I mean is the main difficulty in writing programs in assembly language is the use of variables. Of course, you can use variables in the memory, but they are very costly because you have to produce outputs, produce the address data, then go and fetch and bake, and this will be, extremely slow. But instead, if you plan carefully, if you write the program carefully, then the assembly program will be running extremely fast, and all calculation intense programs will be running efficiently. So what are those registers? I said that the number of registers are limited and very few. We haven't got so many registers. They are all listed in here in this slide. They are general purpose registers, segment registers, flag registers, and pointer and index registers. We group them into 4 different groups. General purpose registers are called AX, BX, CX, and DX. They are AX, BX, CX, and DX registers are 16-bit long. So we can store 16-bit information into the general purpose registers AX, BX, CX, and DX. So we have got only 4 data storage space inside the 16-bit data storage place inside general purpose registers. However, we are lucky that those general purpose registers can be used in storing 8-bit only. So if we give up, if you don't use those 16-bit, but if we can divide up into 8-bit sections, then the number of registers will be doubled. So the registers AH, AL, BH, BL, CH, CL, DH, and DL will be used. All those registers from A to D, from H to L, we have got 8-bit registers. 4 16-bit registers, so general purpose registers could be 4 plus 8, 12 different registers we can define. AX, BX, CX, DX are 16-bit. H and low parts of them will be 8-bit long registers, and these are called general purpose registers. In the meantime, there are other registers which is 16-bit long, segment registers, flag registers, pointer and index registers. These are 16-bit registers, and they cannot be divided into halves as in the case of general purpose registers. So we use CS, DS, ES, and SS for segment registers. And I will be talking about what segment means soon. And flag registers, it will be controlling the operations. If you remember, when I was talking about interrupt, there is a bit inside flag register which controls whether we are allowing interrupt or not. And pointer and index registers are crucial. They are stack pointer, base pointer, source index, destination index, and instruction pointer. So 5 of them. There are 5 pointer and index registers. These are responsible to carry together with segment registers. Segment registers plus pointer and index registers are helping us to obtain the physical address of a memory space. So they usually combine together. So even though you're allowed to use pointer and index registers separately for your programming purposes, you are not allowed to make changes in direct changes in CS, DS, ES, and SS segment registers. So pointer and index registers can be used to store, not instruction pointer, sorry. Stack pointer, base pointer, source index, and destination index can be used for storing data as a variable, but not the instruction pointer. And AX, BX, CX, DX registers together with their 8-bit counterparts, you can use them for manipulating the data inside the microprocessor. But CS, DS, ES, and SS, and F and IP means instruction pointer, you cannot use them as variables in your programs. We will discuss this later on in detail. So once again, it is expanding the concept. AX registers gets its name as A because of accumulator, BX is from base, CX from count, and DX from data. So A, B, C, D, accumulator, base, count, and data. And you'll see that while looping, when you create loops, the number of times you will be, looping will be counted in C registers. CL register, for example. So those registers are used specifically in some instructions. So you are not free to use them as you wish. Even though I say that you can use them as you wish, but there is no way that you can use loop instruction without help of CL. So while programming, you have to be careful of this. And this group is called data group in the meantime. SP, BP, SI, DI are getting its name from stack pointer, base pointer, source index, destination index, and instruction pointer. These are the initials. That's why SP, BP, SI, DI, and IP names are given to those registers. These are pointer and index group registers. And they are really, every single one of them has got an importance in certain instructions. As we examine the instructions over the course time, and you'll see that source index and destination index has to be used in string operations, and stack pointer and base pointer has to be used to reach a certain part of memory. There is no other way Without using them, you cannot reach that part of memory, etc. Flags are showing us the status of some operations, and also it allows us to control some of the operations. So flag registers are extremely important, and we will give I will be discussing it later on. Now the segment group: extra segment, code segment, ES extra, CS code segment, DS data segment, and SS stack segment. Segment registers are used to divide the memory according to their usage purpose. For example, in code segment, there is only code of your program. So you cannot define any variable in code segment. Everything is separated. Everything is isolated. The code, the program code, will be in code segment. The variables you need to define when in your code you define some variables. Those variables will be in some part of another part of memory, which is called data segment. So all the variables, when you write a program in C, the code itself, the executable code itself, will be residing in code segment. All the variables you define will be defined in data segment. If you are using strings or arrays, large strings, those variables will be residing in extra segment. So every type of variable has to be located in different part of the memory, not to interfere the original code and the data. By this way, an isolation will be possible. So what we should know that I'm not talking about assembly language, I'm talking about programming altogether. The source code, the code will be always in code segment. The variables, not the arrays or list, not arrays, strings. The strings and the long arrays will be created in extra segment part of memory, and the basic variables like X, Y, Z, whatever you call them, they will be created in the data segment of memory. And please don't forget that the whole memory for 8086 microprocessor, the length of the whole memory is 1 megabyte. So we will have pages on that one megabyte memory. Those pages will be called extra segment, code segment, data segment, stack segment. Of course, during the from the programming, if you remember, during function calls in C, you have to remember where the call has been occurred, and so you have to store the memory location that when you finish the operation in function, you have to return to the point where the function has been called. So in order to remember where that function has been called, will be stored in stack segment. We will be pushing the necessary information to regulate the normal flow of the program. Every call needs to push some data into stack, and when you return from function calls, you have to pull the necessary addresses and necessary information from stack. So push and pull operations will be carried on stack segment. Now, in detail, AX register, it is called, as you know, it is the accumulator register, and it can be used in 3 different ways. You can use them either 16-bit register as AX or 8-bit register 8 AH or AL. So AX register has got three. When I say AX register, actually AX register section can be used three different ways. Two 8-bit registers, one 16-bit register as AX, AH, AL. These are the accumulator registers, preferred registers to use in arithmetic logic and data transfer instructions. They have to be, it has to be used in multiplication and division operations. As I told you before, every register, certain instructions requires certain registers. So it has to be used, it must be used in multiplication and division. So while storing data inside AX, you have to be careful that if you call a multiplication or division operation, the content will be changed, then the data you need will be destroyed. It also has to be used in input-output operations. There is no other way that you can use, you can get data from input-output devices. You have to use AH, AL, AX registers if you carry out input-output operations. BX registers, the base address registers. It is as in the case of AX. BX is divided into two 8-bit registers, BH and BL. CX is the count registers. As I told you, I don't want to say it can be used as CH and CL, DX for DH for and DL. I don't want to repeat this all the time. As you know, the general purpose registers can be used either in 16-bit mode or 8-bit mode, and they have got different names. Anyway, CX register is used iterative code segments using the loop instruction. As I told you, it has to be used in the number of times that you are repeating the operation has to be counted in CX register. Repetitive operations on strings with the rep command needs CX registers, and count of bits to shift and rotate has to be stored in CX register, CL register. So what we know from here that, as I told you before, all those general purpose registers are combined with some certain instructions, so you are not completely free to use them. If you are executing, if you need an instruction, for example, loop, so you have to set up count register first in order to tell the loop instruction how many times that loop to be executed. Similarly, the data register, it is used for multiplication and division operations, and also it is used to generate the input-output operations address information. So they are specific to those certain operations. Pointer and index registers, maybe the most important one. Let me check the slides. Instruction pointer, I haven't mentioned it anywhere. The most crucial one is the instruction pointer. Instruction pointer is telling the microprocessor, together with code segment, the content of code segment plus the content of instruction pointer will be, we have to add them up in a certain way. I'm emphasizing that in a certain way to obtain physical address of the memory space that we should be fetching data or writing or reading data from that memory space. So instruction pointer, in order to get the operand from code segment, we have to use instruction pointer, and after reading one instruction, the content of instruction pointer will be automatically incremented by microprocessor itself. And stack pointer, base pointer, source index, and destination index, the other pointers and index registers. Source index registers can be used for pointer addressing of data, and it has to be used for string operations. Also, in some certain addressing modes, you will see, I mean, we will be talking about addressing modes in the next week. And you'll see that in order to reach certain parts of the memory, we have to use source index or destination index to reach some certain parts of the memory together with data segment. And destination index registers are used for extra segment as well, and both they can be used as to store data, or they can be used to reach certain parts of the memory, depending on the operation, depending on the process you are doing. If it's a string process, source index and destination index is used to reach certain parts of extra segment. Base pointer, once again, it is used to access data, but this time in the stack segment. And it can be an offset data for the stack segment once again. And if you are not using stack segment for storing data in your program, you can use base pointer as to store data. Stack pointer always points the top item on the stack, so it has to be used in conjunction with stack segment. So SS register. So SS register plus SP register will be giving the physical address of the top of the stack currently you are using, and an empty stack will start from. For an empty stack, the SP register will be FFE, because the stack operations are 16-bit operations. Now the flag register. To be honest, I don't want to go into this one because it will take a lot of time. Let me check the other stuff we talked about. I think what we should do, we should stop here because anyway, let's talk about flags and we can carry on later on. And the rest of this will be the last slide that we are discussing in this class. The remaining part of the slides will be, I will be talking about them in next week. Okay, this is the content of flag register. Flag register is 16-bit long, and it starts from 0 till 15, total 16 bits, and certain bits has been assigned to certain operations, certain information. It stores data to control or show the status of that operation or the condition of microprocessor, and everything, all this control and status, not signals, but the information is stored in flag register. What I'm talking about, let me introduce you. It is just an 16-bit register. It consists of data flip-flops, you know that, and the 0th bit is stored to show us the carry flag. It is called carry flag, by the way. And this flag, whenever, if we do an addition or subtraction, let's talk about addition first. If we carry out an addition, and after that addition, if there is a carry, then carry flag will be set. Otherwise, it will be 0. Therefore, whenever there is a carry in an addition operation, carry flag will be set. Otherwise, as I told you, it will be 0. By the way, I'm checking my notes. Okay. And auxiliary carry, it is similar to, by the way, carry flag is not only used for addition, also it shows us the borrow case in the case of subtraction. If we do subtraction and pardon. Hocam online dersteyim şu an. Acil bir şey var mıydı? Dışarıdayım, evdeyim hocam şu an. Olur hocam, olur. Tamam, görüşmek üzere. Tamam, sağ olun hocam. Öğleden sonra arayabilir hocam. So carry flag is responsible to show us whether a carry out has been occurred during the addition operation or a borrow case has been occurred during subtraction. So both carry and borrow operations, carry and borrow conditions will be indicated in carry flag. So whenever you carry out an addition operation, microprocessor automatically puts 1 or 0 to carry flag to say that after the operation a carry has been occurred. If it is 1, that means there is a carry. If it is 0, it means there is not carry, so everything was fine. The result is just enough to stored in the specified registers. So bununla ilgili sormak istediğiniz herhangi bir şey var mı arkadaşlar, carry flag ile ilgili, eğer dinliyorsanız?
Yok hocam, benim sorum.
Tamam, teşekkürler. Auxiliary carry is not very much, exactly same as very much like carry flag, except the operations and the carry operation is from the nibble. You know, if there is a carry from the nibble, you know what nibble is. If we are doing an 8-bit operations, if there is a carry from the nibble, the lower part of the lower 4 bits of the numbers, if there is a carry from the nibble to the next nibble, then this flag will be 1, otherwise it will be 0. So as the name indicates, it's yardımcı carry, auxiliary carry, harici carry. Some may say that why on earth we should need an auxiliary carry, but you'll see that while doing calculations, sometimes you use hexadecimal codes rather than binary numbers, or rather than, I mean, because we cannot use decimal numbers. So while doing the additions, maybe we are using BCD codes. So we are reading BCD codes, BCD, you know, binary coded decimals. And we read binary coded decimals from the keyboard, and then we store them as it is, and then we carry out those binary coded decimals in the memory, and we need to add them up together, and during that addition we realize that, I mean, if it is a binary coded decimal or if it is an hex code number, then if you need to know whether there is a carry from the first digit of binary coded decimal to the next digit of binary coded decimal, then you need that auxiliary carry information, and that's why this is signaled. This has been set 1 if there is an carry. Otherwise, it will be set to 0 by the microprocessor itself. And so the next one, there is a parity flag. Parity flag is showing us the number of ones, the total number of ones in the microprocessor, so in the register, if we carry out an operation, and the result will be consisting of, the result will have numbers, will have ones and zeros in the register, the output, how can I say? We will carry out an operation, let's say an addition, and there will be an result. That result will be consisting of ones and zeros. So with the parity flag, we are looking at the number of, total number of ones inside the that register, the resulting register. Parity flag is set if the result produced by the instruction has even parity. That is, if it contains even number of bits at the one logic level. So it means that if the number of ones are even, for example, if it is, there are 4 ones and 4 zeros in an 8-bit operation, the result is 8-bit, and the number of ones in that 8-bit result is 4. When you add them up, 4 is an even number. So in this case, parity flag will be 1. Otherwise, it will be 0. If the number of ones in the result is odd, in this case, the parity flag will be 0. This can be useful in some operations, especially during the communication between the outer devices. You may, the resulting data may be distorted somehow. So we have got, in digital design course, I was showing parity coding, parity bit. I was adding parity bit to the beginning of the code. So before sending a data through the communication line, we check the parity of that information, that data, and put that parity information to the beginning of the data we are sending through the communication line, and at the end of the device, at the end of the communication line, gets the data and checks the parity bit. And if the number of ones are verified by the parity bit, depending on odd or even, then it assumes that the communication channel was good and the data hasn't been corrupted, etc. And so you may think that why should I need the number of ones information, whether it is even or odd? It has got certain usages during the programming or during the communication, so it has got some importance. Maybe not nowadays, but still there are some, in some programs you may need that. So we covered carry flag, parity flag, and auxiliary flag. And the next one is a zero flag. Zero flag is quite straightforward. Zero flag is set if the result of an arithmetic or logic operation is 0. Otherwise, it is reset. So whenever the output result, the operation, whenever the operation of an arithmetic or logic operation contains complete zeros, if all the bits are 0, then the zero flag will be 1. Otherwise, it will be 0. So if the 0 flag is 1, then we will understand that the output of that operation produced 0. And sign flag, the next one is sign flag. This flag shows us the most significant bit of the result, and this is directly copied into sign flag. If sign flag is set, the result is negative, or reset, it is positive. So any number, for example, let's say 8-bit number we are using, 8-bit binary number, the most significant bit, in this case the 7, because we are giving the numbers from 0 till 7, so the most significant bit of a byte will be showing us the sign of a flag, sign of the number. If it is 1, we understand that that number is negative. If it is 0, we understand that that number is positive. That value is positive. So it has been indicated by sign flag. Data flag. Direction flag. Direction flag. Let's go interrupt flag first. If you will remember from the interrupt inputs I was talking about, if we set 1 to interrupt flag through the instructions by software, we are capable of setting this flag either 1 or 0. If we give 1, then it means we are allowing interrupts from external devices. If it is set to 0, we are not allowing the outer devices to interrupt us. Okay. Direction flag. Let's talk about direction flag. It is used to manipulate the strings while doing the string operations. As I told you before, the direction of the operation, because in a string operation, let's say there are 16 characters in a string, and each character is 1 byte long, as you know. So while, for example, if you want to compare one string to another, how we will be comparing these two strings, from end to the beginning or from beginning to the end. So depending on your choice, depending on your direction choice, the operations will be carried out on that direction. This can be important in your, how can I say, this could be important to speed up process. For example, just a simple one. For example, if you want to compare the passwords, a defined password, and the password has been entered by the user. I'm just making up this example. For example, you require 20 bytes information for password, but the user entered only 3 of them or 4 of them. If you start from the end, you will see that it hasn't entered any information for the first byte, and you will directly reject it. You don't need to carry it. Or imagine that you require 20 bytes and the user enters 19 bytes. If you start from the end, the user's last byte will be empty. So from the first comparison, then you'll say that the password is not correct. Of course, that's just a mock-up example, so it doesn't mean anything. So direction flag tells the string operations which way the string has to be processed. The logic level of direction flag determines the direction in which the string operations will occur. When it is reset, the string instruction automatically decrements the address. So decrementing means, so we are processing from end to the beginning. When it is, therefore the string data transfer proceeds from high address to low address. On the other hand, setting direction flag causes the string address to be incremented. In this way, transfers proceed from low address to high address. The next one is the trap flag. If trap flag is set, the 8086 goes into the single step mode. When in the single step mode, it executes one instruction at a time. This type of operations is very useful for debugging programs. So if you debug the program, what you have to do, you have to put trap flags. You have to set trap flag, and in this case, every time 8086 will be executing one instruction, then waits for the next step, and then you provide the next signal, and then it executes the next one, etc. So it will be, it is waiting for you to press a button, and by this way you execute it step by step with the help of trap flag. It is just for debugging. Debugging, blah, 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 blah. And the last one is the overflow. When overflow is set, it indicates that the signed result is out of range. If the result is not out of range, overflow flag remains reset. We will be talking about overflow carry, auxiliary carry later on in the instructions while we are I will be introducing some specific instructions. Those instructions will require to revisit the overflow and carry borrow situations. So we will be talking about a lot in the future. But what we should know about overflow, if the size of the register is not capable of holding the result that occurs after an arithmetic or arithmetic operation, in this case, overflow indicates that this result, the result in the register is not a valid one because it contains wrong information. There has been an overflow, so it is not reliable. Overflow information is important in that sense. That's it today. That we should stop from here, and the next week I will be talking about the bus interface unit, how we calculate the physical addresses. That's important because there is always one question comes from here, and then we will talk about addressing modes. After that, we will start. I will start introducing the instruction set. That's all for this week. Efendim bu kadar. Kaydı durduruyorum bu arada.
Teşekkürler hocam.
Kusura bakmayın, dediğim gibi modum çok düşük, yorgun olduğum için.